Object-oriented programming. Thus far in our training, we've been using Python mainly in its procedural paradigm, but as you know by now, one of Python's great strengths is that it's multi-paradigmatic. That is, we can do procedural programming, object-oriented programming, which of course is what we're concentrating in this nugget, and even functional programming for those that are into the so-called meta-programming thing. In this nugget, we're going to lay a formal foundation in OOP principles. We've flirted around with the subject a little bit in earlier nuggets. We're going to flesh it out, build upon it, and then in the subsequent nugget, when we do graphical user interface design, we're going to be transparently applying everything that we learn in this nugget on creating and using classes. There's a lot to learn in this nugget, so let's get going. So what is object-oriented programming anyway? OOP we're going to contrast with procedural programming, which we've done largely in this nugget series so far. Procedural programming is where you're pretty much structuring the flow of your application from start to finish and then trying to capture any edge cases, any sub-procedures that the user might decide to go down in your user interface. You'll also recall that the way that we modularize or separate out components of our program in the procedural paradigm is by using functions. Now that's all well and good. It componentizes your program to a certain degree. But what about the issue of code reuse? That is to say, what if we've created a function that does some work for us that's all well and good, but then elsewhere in the program we want to use the same basic function, but perhaps add just a little twist on what it does to suit a different need in our application. As you see here, you wind up pretty much just copying and pasting and tweaking your code on your functions, and you wind up at the end of your application with all sorts of functions. I call them Franken functions that are slightly different. They all have the same basic mechanics, but there's no link among any of them. That is, if we were to update this original function that we used as a template, there's not going to be any inheritance by the other instances of that function in our code. You see? So procedural is a really nice programming paradigm. It'll get the job done, but the main reason why folks tend to be OOP nowadays is because instead of just a row of functions, we can then create objects that are freestanding and or relate to each other, and each object has encapsulated within it its own functions. We know by now that functions inside of classes are actually called methods, and other attributes, you see? So you wind up with these self-sufficient containers called objects, and what's nice about these class objects is that we can just spawn as many instances of each object as we want to in our code. As a matter of fact, there's an important aspect to object-oriented programming design. In fact, it's more than an aspect, it's what's called the design pattern. And what design patterns are in object-oriented programming are different schemes for implementing OOP in a development environment to solve your problems. I would specifically recommend you check out the O'Reilly book, Head First Design Patterns. I've read a lot on OOP design patterns, and that book tends to be the most approachable for those who are beginners in this subject. Alright, so what else about OOP that differentiates itself from procedural programming? Well, in OOP we can really boil the syntax of it down to just this guy right here, object.attribute. We've been using this so-called dot notation a lot in the course thus far. Even aspects of Python that aren't ordinarily considered OOP actually are. You might recall that in Python 3, when you run the type function, you wind up with class equals string, let's say. Let's say you've created a name called foo, and then you run the type function and pass in that A, you're going to get class equals str, because under the hood, the actual design patterns of Python itself is OOP now. There's really not much of a way that you can avoid OOP in contemporary programming. So we use this dot syntax, as previously discussed, to access the attributes of an object. Now, some of the terminology gets a little bit muddy here in Python. For instance, you might have a class object that you've instantiated that you then can use dot notation to call methods or functions that operate on that object. You also can use dot notation just to define what are called properties or characteristics of that object. All right? More on that in just a little bit. The bottom part of our whiteboard here shows us the relationship among objects in an object-oriented programming paradigm. One thing you're going to have to understand about this inheritance deal is that in objects we have encapsulated within it all of its core functionality. So we start with a class, which, as we've discussed in the previous nugget, is more or less an instance factory or a template for creating other objects. And in that superclass, we have methods and attributes that are encapsulated within this object and are usable immediately by instantiating or creating an instance of that class. What's also especially flexible about OOP is that you can avoid this problem that we saw over here with functions where we have similar functionality required and we just wind up manually modifying copies of a base function. In OOP, we can do what's called a subclass, which is kind of the equivalent of doing a file save as operation in an Office productivity application, where you have all of those methods and attributes that are contained in the superclass copied down through inheritance in our subclass. And remember, a class is not usable directly. A class is used as an instance factory. When we instantiate an instance of a class, that instance becomes an object in its own right, and again with the flow of inheritance. In this case, we have a superclass called A. We've subclassed A as B here in the middle, and then we've invoked an instance of this subclass called C. The law of inheritance says that C now can transparently access all of the methods and properties of both B and A. If you have familiarity with name resolution in TCP/IP networking, you know how the order works, right? A computer will look in its own DNS resolver cache in memory first to look for a name to IP address mapping. Then it'll go to the file system and look up a hosts file and see if there's a mapping in there. And then ultimately, if that client computer is configured to talk to a DNS server, a DNS lookup is performed. Similarly, when we've instantiated an instance of a class and we're actually using this instance in our code, when we call a method, let's say .y, the Python interpreter needs to figure out where that method lives. So what'll happen is you wind up with what's called a tree search, as Python starts with the instance and what it has in its local collection of methods and properties for that matching object. If it's not there, it'll then come up to its parent class, in this case B, and look through its list of methods and properties. If it's not there, we'll go up yet another level in the tree to the superclass on which this subclass was defined and look for methods and properties there as well. Now, one thing that may be coming to your mind is you notice that there's a method called x in the A superclass, and we've also defined a method named x in the B subclass. This deals with the fact that you as a designer can choose to override any of the inherited methods or attributes that come from a parent superclass. All right? You're not stuck with all of those inherited objects. You can redefine them, and we can even do that down at the instance level, define a method called x that would therefore override this guy as well as this guy. Sum total, friends, with object-oriented programming, inheritance and code reuse is the name of the game. I would like to encourage you to use Google Images wherever possible when you're studying a new topic. Certainly object-oriented programming is a good candidate for this because you'll find that you don't have to reinvent the wheel. As an instructor, I don't have to worry about creating all sorts of fancy diagrams that have already been done hundreds and thousands of times before. The diagram you're looking at now comes from adobe.com, their developer network website, that serves as a really good example that shows a base class or a superclass here that contains a couple method definitions, mProcedure1 and mProcedure2, as well as some attributes or properties that pertain to that class. In this particular paradigm, we're not subclassing. It looks like we can immediately begin instantiating instances of this base class, and you'll see all the way around the circle we have instance 1 all the way to instance 8, and you'll notice that by inheritance, they've picked up all of those subroutines, those methods, as well as those properties. So these instances then are freestanding, but at the same time have an umbilical cord, as it were, that connects them to their parent class. such that we can make a change to our class code here, and inheritance will immediately update that on each instance. Now, overriding is important if you don't want to inherit certain methods or attributes from the parent class. In Singapore, there's a university called the Nanyang Technological University, and that's where I found this nice picture. It's very simple and elegant. Here we're starting with a base class called Circle that has radius, color, those might be variables, and then we have some methods: get radius, get color, get area, and toString, which is used in many programming languages like the .NET environment to do a string conversion, similarly to how str function works in Python. Now, in your programming and in your application, this Circle class might get a lot of use. You could immediately instantiate instances of it. However, what if you had types of circles? For instance, a cylinder is a form of a circle, but it has some different properties, some different methods. Well, instead of just building a new base class from scratch, we can subclass cylinder, inheriting from circle. And by default, we get all of those properties and methods, but notice that you can do overrides to strike away stuff you don't need, to modify methods, or just add your own content from scratch. Before we start digging into the demo and start showing you how this actually works in Python, let's take some more object-oriented programming principles and go over these to make sure that we're both clear on them. In Python, the class statement, which you're about to learn about in living color and become familiar with very intimately, creates a named class object. And just like a template in Microsoft Word, as we talked about in the previous nugget, a class is not usually meant to be operated on directly, but instead you call the class object to create an instance of the class. This is like creating a new document in Microsoft Word that's based on a particular template. The template remains untouched, and we then have read-write access to an exact copy of that class or that template. Within a class, you create one or more assignments. These are called attributes. Specifically, attributes can be constant data, variable data, methods, which are functions attached to an object. And then finally, when you do call a class object to make an instance, by default you inherit all the attributes of the superclass or the parent class. And also, this is important, the instance gets its own namespace. That is to say, we can create a class called Circle, just like you saw in the previous example. And then when we want to instantiate an instance of this class in our code, we might do something like this: C equals Circle, and then depending upon whether we were taking input parameters or not, we would just either do open paren, closed paren, or we would add those initial parameters. It's up to you. But now what we've just done is we've created an instance of the class Circle. Really, when you create classes, you're creating your own types. We've gone around the block quite a bit with built-in types in Python like file, string, float, tuple, dictionary, etc. Whenever you create a class in Python, you are in a very real way creating a new data type from scratch. And the namespace thing simply means that we use dot notation to access properties and methods. So in our class, let's say we created a function called area. Once we've instantiated our object C, we could call the area method simply by typing c.area. Again, it's the dot notation that separates the object from the property, attribute, or method. Now let's have a look at how we define a class in Python. It's really quite simple, as a matter of fact. To create a class in Python, which you can do from a module file or from the interactive interpreter, is use the class statement, then the name of your class, which, as I've repeated several times thus far, it's not a requirement, but it's strongly suggested that you use what's called camel case, in which each significant first letter of each word is capitalized. You also can't have space, so we couldn't do our space class. This has to be a single word. And then in parentheses, you would specify the base or parent class from which you're inheriting. Now, you remember when we did exception handling, I recommended that you always inherit from the exception built-in base class. When you're starting a class from scratch in Python 3, what you'll want to do is inherit from the blank slate or tabula rasa, to bring in some Latin, object base class. Underneath that, indented 4 spaces, we have a docstring. This again is not required, but it's certainly important in our class definitions, not just for the overall class, but also for every method within that class that you provide a docstring, such that our users or fellow developers can invoke the help function to read about the class and methods in particular. Best practice is to create a constructor function definition to make it easier when you're instantiating an instance of your class. You can set up just kind of your starter parameters. And we do this by invoking the magic method init, _init, _. The first parameter is always going to be self. Now self refers to the instance that's being created. So in this case we're creating a class called our class. In our code, if we wanted to create an instance of the class, we'd give it a name, we'd then specify the name of the class, and then in parentheses we would add any required arguments. Self is kind of an invisible argument. We would never reference self in our live code. Self is internal, that tells Python that we're referring to this instance, whatever, in this case it would be OC. This init involves 2 arguments that wind up just coming back as straight ahead attributes. So arg1 becomes an object named arg1, arg2 becomes an object named r2, and you'll notice that we're using dot syntax. Self again is a generic placeholder that's going to be substituted in our live code by OC. So we would say oc.arg1 to get back the value of arg1 that was passed into our definition. Same with arg2. So init is again called a constructor, and it gives you your initial set of parameters when you create an instance of a class. Now you're not limited to init. There's a whole lot of other magic methods that you can use to customize the behavior of your class. We're going to talk about that momentarily. But when it comes to actually doing stuff or having your class be able to perform good work, there's where you're going to do your method definitions. And there's nothing magical really about defining a method. You'll notice that the syntax is exactly the same as any Python function, right up to returning values. This guy doesn't use the return statement, but you could just as well do that if you needed to return data out of a function. The only thing that makes a method different from a function is that a method is a function definition that occurs within a class definition. That's all there is to it. So it looks like we have a method called printargs taking self, or the current instance, as its argument, and it's going to simply do a printout of arg1 and arg2. So to repeat, let's do this example again. I'll create a name called oc2, and we're going to instantiate our class, and let's say we put in 1 for arg1 and 2 for arg2. We can then do oc2.printargs, and self means that there's no parameters, so it's just open paren, close paren. And this, of course, is Python 2 syntax. In Python 3, we would need to wrap these calls in parentheses because print is a function. But the result of the printargs function would give us back 1 and then 2. It's as simple as that. For this example, we're using a Python script that I've called classes.py. And in this first example specifically, we're creating a class that will ultimately be a superclass or a parent class. But for now, we're just declaring it as a plain old garden variety class. And let's say we needed a class to define a car object. Car or vehicle is a typical example used when folks teach object-oriented programming. So as expected, we're going to open this header line with the class declaration giving a capitalized or title-cased name of our class we're inheriting from object. I'm putting in docstrings, as you see here, at the class level as well as the method level. Our constructor statement is here, and what we're doing is defining init with, of course, the self built-in argument that always needs to be there. And when a class is instantiated, we want to provide year, make, and model is just base information. Generally speaking, most Python programmers will then take those input parameters or those arguments and create names out of them. So I'm creating self.year as a string representation of year, self.make is make, self.model is model, and just for grins and to show you that it can be done, we can add constants in here as well. And in this case, we're creating self.static, which is an attribute or a property that will always return the string constant car data. This middle guy here, I'm getting a little bit ahead of myself. There are plenty of built-in magic methods, as methods we know that start and end with double underscore. And one neat thing about these when used in object-oriented programming is that you can format your classes the way you want them formatted. In other words, what happens if we instantiate an object of car like we're going to do down here, create an NS name, and then what happens if the user or we in our code need to do this? Because by default, this guy is going to come back as a class object, not as a string. And as you know, sometimes data has to be in a particular format to do something in your code. So if we do an strns on a class object, is the code going to blow up? Well, to make sure that that doesn't happen, you can use the magic method str, passing in self, and in this case, I'm returning using C-style string formatting, a line that's going to say string representation is string, 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 self.year, self.make, and self.model. You see? And you can do the same thing if you're working with numbers and you want to make sure that the float works okay, integer. The magic methods are excellent for customizing any conceivable attribute that you need for your class. And then finally, I'm creating an actual honest-to-goodness method here called printCar that frankly, in a sense, does the same thing that the str magic method does. This is going to echo back the full name of the vehicle. And just to spice things up and as a point of review, I'm using the Python 3 string formatting where we call the format method on a string using the curly braces and the positional numbers and passing in again self.year, self.make, and self.model as the objects. Finally, just as a bit of what's called cruft or unnecessary code, but important I think to show you that it can be done, we can invoke the static data, our constant data, very easily using dot notation. I'm also going to have this printCar function print the value of self-static just to show off an attribute fetch. Good deal. Now in this first example, we're going to run the script from here. Then I'm going to show you, which is pretty much what you'll be doing in the real world, using the class as an import object. So in this first example, though, we're going to define a name called NS that instantiates an instance of car, and we're bringing in 1990 Nissan Sentra. We'll then display a string representation of NS. Then we're going to print NS. Then we're going to print out ns.static, and finally we're going to run the printCar method, again using dot notation. So to kind of walk you through what happened, we defined a name called NS and we passed in 1990 Nissan Sentra. The next thing we did is run the str function against NS, and it gave us back our custom string format. After that, we just did a print of ns.static, that was our constant car data, and then we finished with a run of the printCar function, which you'll remember gives us the full name of the object and also, just for cruft's sake, gives us a run of the static data again. Let's now restart the shell to clear out all of our names, and let's import classes. Now, the fact that it ran through the code like this should be no surprise to you, because you'll remember the way module imports work, unless we're doing the main trick, that Python upon import is going to run every line of code in that file. And since we had this stuff here, it makes sense that it's going to run it. So what I'm actually going to do is come back, and why don't I just comment out these lines using the triple quote, save the file. We'll come back to Python shell, restart the shell again, and let's import classes, suppress that code, run a dir on classes just to see what we get back. Remember, classes are given first, so we have car, then we have our magic methods, and then we have any standalone functions. You can call the docstring for a class or for a function just by using the dot notation and also invoking the appropriate magic method. Double underscore doc double underscore gives us that. Of course, we could do just the same thing with the help function, which is syntactic sugar for the doc magic method. That actually gives us more information. Running help on classes.car gives us the class docstring, gives us our methods, init, string, and printCar with our documentation that we've added to those. Good deal. So let's create another object. I'll call it ns2, and this time let's supply 2004 Honda element. And of course I ran into a glitch here because I didn't use the full namespace, did I? If we were using from classes import car, that would have worked. But we just imported all of the names, which maintains the existing namespace of the classes module. So I have to prepend classes to car to get this to work. If I run a type on the NS2 object, it tells us that this is a class, and it gives us the object name of that class. Classes.car is the parent class here. Now, if we did a str on NS2, we get back our custom handler. We can fetch any attribute we want here just by supplying the proper namespace. We can do an ns2.year to get back the year, ns2.make to retrieve the value of that property, ns2.model is element. Now what if we wanted to make a change here? Can we override inherited values? You know we can. How's that? ns2.year equals 2010. And you notice that we get back an updated value there by making that change. What about ns2.static? No problem. Let's run print car. ns2 dot any IDE worth its salt is going to give us a list of the attributes and methods that are available. You see print car is in that list, and it runs the function with the update that we overrode from the parent class. Let's talk a little bit more about these Python special methods or magic methods that we can include in our class definition to customize the behavior of instances. We already saw how we can use _str, _ to manage string conversions. We also have REPR that does the same thing. Generally speaking, the REPR gives a more accurate string representation than str. However, str tends to be the more popular way to do string conversions. Another popular special method you'll see are the mathematic-oriented ones. In other words, what happens if you create two instances and perform addition, multiplication, modulo division, straight integer division, etc.? Well, you can provide function definitions that modify that behavior using these magic methods. Add for addition, sub for subtraction. Before I show you the sample code, let's go out onto the web one more time and look at the Python reference manual. You can get to this, as you know, through docs.python.org. We're looking at the 2.52 reference manual, but the same thing exists in the version 3 one as well. But the article you're looking for is called Special Method Names. It's really nicely specified here. Basic customization, customizing, attribute access, and it gives you a detailed run of the syntax behind all of those magic methods. To finish this slide, let's look at a sample class declaration here. We're creating a class called bar, foobar, spam eggs, the whole deal. And also, as expected, we have our constructor definition that involves just one formal input parameter, and we're setting self.a equal to a. In other words, just to create an object of that argument. To handle addition, we can add a method using add that involves another argument, in this case b. And in this add method, we're defining yet another name and returning that name out of the function called s that simply performs addition of the representation of a, self.a, and also, check this out, this can be a little confusing at first. We're taking b, the second addend, and we're applying the a property to it. So in other words, we'd wind up with b there. b.a is equal to b. And then, as I said, we're returning that value. So in our code, we could create, say, a name called x, where we invoke an instance of bar with a value of 10, a name called y that creates an instance of bar with 20, third name that takes x plus y. That works okay because of this add magic method handler. And then if we print the value of z, we get 30. Pretty straightforward. Works the same way for all of the other mathematic-related handlers. In this final demonstration, I want to show you how to subclass. The reason why we'd subclass, of course, is to take advantage of the encapsulated attributes and methods in a base class and reuse those through inheritance. So we have our car object, and that gives us make, model, year, etc. Does some pretty basic stuff. Let's say we also want to create a class or another object to embrace motorcycles instead of traditional four-wheeled vehicles, which are embraced with car, let's say. Well, we could either create this motorcycle class and inherit from object and recreate all this stuff, or very simply, we can subclass motorcycle and inherit from car. And how you do that, as you already know, is to use the class statement. We provide the name of the class and then the parent class from which we're inheriting. You also know that we can use pass as a way to just kind of put on ice that function, method, or class definition and we can do code with it later. Pass is useful in our case today because all we're going to need are year, make, model, and static, which come to us through inheritance anyway. You see what I mean? From the interpreter, we're not going to run the from import type. We're actually going to import everything from the class's library that we've done. And let's create a name called MC. That's an instance of the motorcycle class. Because motorcycle inherits from the car class, we're going to need our 3 parameters, aren't we? So let's do 2008 Honda Shadow. And again, we run into the name qualification issue. You probably saw that before I did, didn't you? Gives us good practice, though. If we invoke the dot notation and pause for a moment to let the Python shell or the idle IDE give us our methods, notice that we can access make, model, year, we can pull static, as well as the print car function. In other words, we've inherited everything from the parent class. mc.static, and just as we saw before, no big surprise, we can redefine any of this stuff to our heart's content. Simple as that. Object-oriented programming review. In this nugget, we formally defined object-oriented programming and compared it to the procedural paradigm that we've used for most of the course thus far. At this point, I hope you're familiar with what a class is, how inheritance and encapsulation work, how we can subclass an existing class, instantiate instances of a class, etc. The whole deal. As I told you at the beginning of this nugget, we'll be able to get some more practice with OOP principles in the following nugget, in which we cover GUI, or Graphical User Interface Development. I hope that this has been informative for you, and I'd like to thank you for viewing.